Okay, I think we are ready to start. Good afternoon, ladies and gentlemen. I'm Magdalena Skipper. I'm editor-in-chief of Nature, a weekly scientific journal. And it's my enormous pleasure to be spending half an hour with Professor Shinya Yamanaka. And we will have a conversation. We'll see how we do for time, where there is time for open for questions from the floor at the end. But let me introduce Professor Yamanaka first. He is director of the Center for IPS Cell Research and Application and a professor at the Institute for Frontier Medical Sciences at Kyoto University. He also has an affiliation and ongoing research at UCSF, at Gladstone Institute. And of course, Shinya is best known, probably best known, for identifying so-called IPS cells, induced pluripotent stem cells. And I'm sure you all know that in 2012, he shared a Nobel Prize with John Gurdon for, and I quote, the discovery that mature cells can be reprogrammed to become pluripotent. And of course, the study of cells has a very long history. Ever since we were able to magnify objects, we were interested in understanding these building blocks of living organisms. And probably many of us who have a background in life sciences think back to the invention of the microscope and really the taking off of that insight in the 17th century. But for a very long time, we believed that once cells were differentiated to create the organs of an adult organism, that was the final fate, and that could not change. And indeed, your work led to us rethinking that under special conditions, that could indeed change. There is so much to discuss around this topic because of course, the topic is not just a theoretical, philosophical consideration, can we reverse differentiation of cells, but it has very important implications for therapy. But before we get there, I would like to spend a couple of minutes talking about you and your path to your present position in your career. So your most famous contribution to research and indeed therapy happened in the lab, but you did not start as a research scientist, right?
Yes, actually, I started my career not as a scientist, but as a surgeon 30-some years ago.
Yes.
Especially, I was working on orthopedic surgeon because I love sports, so I was very interested in sport medicine. Mm-hmm. So that was my first goal of my life. But I changed my career.
So how come? What was it that took you from a surgeon who was interested in sports medicine to actually addressing quite a fundamental biological problem?
Well, the biggest reason was that I was not good at surgery.
Lesson number one, recognize your weaknesses.
And the second reason was that I lost my father when I was residency. My father suffered from hepatitis C. At that time, there was no cure. So that was one reason why I thought I should become a doctor. I really wanted to help my father, but I couldn't. I couldn't do anything for my own father. So I felt very powerless or useless. I became a doctor, but I couldn't do anything for my father. And also, I couldn't help many other patients suffering from intractable diseases and also injury, like spinal cord injury. Mm-hmm. So that's another reason, because I firmly believe that it is science that could help those patients suffering from intractable diseases and injuries. Of course, not now, but in the future. Mm-hmm. It takes some time, but science can overcome diseases. So that was my motivation right now.
And so tell us a little bit more about iPS cells. And ideally, they are, of course, not the only cell-based therapy or technology promise. Tell us a little bit more about their potential.
Yes, so I spent some time in San Francisco as a postdoc, as a young researcher. And I learned about embryonic stem cells derived from, at that time, mouse embryos. So embryonic stem cells, known as ES cells, are something like super cells. They can proliferate forever. They can expand as much as we can expand ES cells as much as we want. Then we can differentiate ES cells into any types of cells, like brain cells, heart cells. But when I was in the States, late 90s, we only had mouse ES cells. But after I came back to Japan in 1998, human ES cells were developed by James Thompson. It was a huge breakthrough to have human ES cells. Because just like mouse ES cells, human ES cells we can expand human ES cells as much as we want. Then we can convert human ES cells into, once again, brain cells, heart cells. So for the first time in human history, we can prepare any human cells in a large quantity, anytime. So there is a huge potential of human ES cells in cell therapy and also in drug discovery. But one hurdle of using human ES cells was the usage of human embryos. There was and there is still a very high hurdle about the usage of human embryos. So that's what was going on around year 2000. And at that time, when I was like 37 or 38 years old, I got my first own laboratory in Japan, in Nara. I was very happy. But I had to set a long-term goal of my own laboratory because I want to recruit young students and young fellows. So I had to have an attractive vision. So I thought very hard, and I thought, well, human ES cells were wonderful, but we don't want to use human embryos. So if we could convert our own like skin cells or blood cells into embryonic-like stem cells, that would be wonderful. So that's why I started working on, at that time, there was no name such as iPS cells, but that's why and how I started working on this project.
But this was a very bold idea because, of course, at that time that you describe, it was generally believed that it was not possible to achieve this in organisms such as us. We knew, of course, about regeneration, for example, in amphibians, right? We all know about tails that come off, salamanders, for example, that can be regrown. But it was generally thought that in mammals, such as us, this was not possible. So I guess what I'm trying to tease out of you is, where does the boundary lie between audacious dreams in research and still having a balanced program of research where you're responsible for careers of other people in your lab?
Yeah, so when I started this project in 2000, we knew it should work, at least in theory, because just like 2 years before my first own lab, in 1998, Professor Sir Ian Wilmot in Scotland, he created a new sheep from a differentiated cell by cloning. So it was a very technically challenging, but actually he succeeded. So he succeeded in reprogramming adult cells back into the embryonic state, although the success rate was extremely low. So at least we knew it should work. But I also understood very well, knew very well that it should be extremely important. But when I tried to recruit students to my own lab, I didn't tell them anything about difficulties. I just told them how wonderful it would be if we succeed in making this project.
Yes.
And this strategy worked. 3 students joined to my lab, and they become very first students of my lab. So I was very lucky.
That's fascinating because, of course, the technicalities of creating the sheep, famously known as Dolly, were really very different from what we now call iPS cells. So you were really investigating what was the minimal requirement to add to these differentiated cells, to change them, to reprogram them to that basic state.
So I had a very simple mindset. I would say it's a surgeon's mindset. Why don't you try? Don't think too much. Why don't you try? That was, I think, maybe you would agree. We have a great orthopedic surgeon here in this room. I hope you would agree with me. But that is surgeon's mind. And I think it is very good for doing risky projects. If you think too much about risky projects, you cannot start. Because there are many reasons why most likely you would fail if you think too much. But in my mindset, I wouldn't think too much, and I just try and try.
This is very interesting. Fantastic advice to researchers who are thinking about taking their research on the sort of path to breakthrough. But I'm sure this absolutely translates to pretty much any walk of life. If you consider the risks too much, you end up talking yourself out of the proposition in the first place. So very useful advice. So what about
I'm not sure it's really useful or not. Sometimes it's very
yes.
too risky.
So what about the next steps? Because we're talking here about taking cells, and I think using the example of skin cell is very illustrative, and reprogramming those cells so they can become something else. But in order for that to be therapeutically useful, usually you have to wait for the next step, for example, or some aspect of tissue building or organogenesis.
Yeah.
Where are we with this in the current state of knowledge?
So before we generated iPS cells, my group was very small. Actually, iPS cells were generated by only like 3 or 4 young scientists in my lab. But once we generated iPS cells, the situation became much different. We have to collaborate with many other scientists and also with many other physicians in order to bring this technology to patients. So we generated human iPS cells in 2007, November 2007. That's the date when my life was really reprogrammed. Because I'm still a scientist, but what I'm doing right now is very different from what I used to do. Before human iPS cells, I did many experiments by myself. I wrote many papers. That was my main job. But after after generating human iPS cells, I became kind of CEO of a small company from a startup. So I have to recruit many different talents. I have to raise money. I have been spending a lot of my time in fundraising. So it's really a different type of job.
And did you have any support? Because this range of skills you describe is not the usual skill set that a surgeon or certainly a researcher would have.
Well, I have many friends, fortunately. To be honest, as I mentioned, I was terrible at surgery, but I'm confident I'm terrible at business. Because my father was a businessman, and also my grandfather was a businessman. They had a small factory, and I was only son. So I was supposed to take over his business, but he told me, you should not take over my business because you are not talented at all. You should become a doctor. I don't know why.
No.
Maybe I'm too honest. I don't know. I'm sorry, just joking. So when I started this new job, it was very challenging. But fortunately, many friends came to me. Some of them are in this room. They are CEO of huge companies, and so they taught me what I should do. So I owe them a lot. Yes.
That's another wonderful lesson, right? Recognizing one's own weaknesses, and then
Yes.
either having friends who can complement them, or collaborating with those who can synergize with our own positive and maybe not so strong qualities. So you said, you used this wonderful phrase that in the year 2007, your own life became reprogrammed. And then actually very quickly afterwards, you were awarded the Nobel Prize
Yes.
For this discovery. And so often Nobel Prizes take a very long time to be awarded for those discoveries, and here it was just a matter of 5 years. I have to ask you, because I'm sure everybody here in the room is curious, how did you hear? Were you expecting the news? How did you hear? And to what extent was this a second phase of reprogramming of your life once you were awarded the
Yes.
prize?
It was. So I was invited to Stockholm many times before 2007, every year. So I was able to sense that I was being nominated.
Right.
So like year 2005 or 6, every year, Scotland newspaper made a prediction who will win. And in 1 year, I believe it was in 2005, I was at the top of the list.
Okay.
But I was not awarded. And next year, so it is Karolinska Institute who decide who should be awarded. So in 2006, I was asked by Karolinska Institute to be an advisor of Karolinska Institute. But I was very busy. I was trying to bring iPS cells to patients, so I declined.
Okay.
They were very surprised. Are you sure? We are Karolinska Institute. Are you sure you want to decline our offer? And I said, yes, I have another obligation.
You did say you were very honest, right? So
Yeah, yes. So because I declined that offer, I thought I would not be awarded for next 10 or 20 years. So in 2011, October, I forgot the exact date, the day of the announcement, it was a national holiday in Japan. So I did not expect at all. So just like today, I ran outside today, actually. I'm crazy. But 12, I was also running, like 20 kilometers. But my secretary was in my office, just in case. So as soon as I came home from running, my secretary called me. And she told me, Professor Yamanaka, we just got a phone call in English. And they asked your personal phone number. So, okay, that I don't know what that meant. So I changed my clothes, and my wife asked me to fix the washing machine. So I was working very hard.
Of course, clear set of priorities.
Yes. Then I got a phone call in English. And he said, Professor Yamanaka, we decided to give you this year's Nobel Prize. And to my surprise, he asked me, would you accept? That's very surprising. So I answered, yes, why not?
This time.
Yeah, that's how it happened.
Wonderful. What a wonderful story. I'm just trying to imagine what's the proportion of Nobel Prize winners who received the phone call while fixing a washing machine. It's something to keep in mind.
And the Japanese government was very nice. As a gift to celebrate my Nobel Prize, they decided to give us a new washing machine.
Very, very thoughtful.
Yeah, it's a true story. Because I couldn't fix it.
Well, here's a man who can win a Nobel Prize who can't fix a washing machine. But there you go. So I really like, I mean, there is nothing not to like in anything that you say, but I really liked the fact that originally you declined this offer to be on the board of Karolinska Institute because the patients were taking the priority.
Yeah, actually, I was very busy. Very busy. So to me, it was more important to advance the technology. And I thought maybe like 10 years or 20 years later, if and when we successfully bring this technology to patients, I maybe receive Nobel Prize, and that would be wonderful. So it was actually much earlier sooner than I expected.
Yes.
So it was, of course, it was wonderful, but it was the beginning of my how to say, my hard works, another kind of hard work, because I felt much more responsible for patients. I really want to help patients, but so far I haven't helped any patients so far.
So where are we at in terms of clinical application of this cell-based
So we are at the entrance of clinical trials in multiple applications, such as Parkinson's disease, retinal disease, corneal disease, heart disease, spinal cord injury, like platelet. We can make platelet, blood cells from iPS cells, and we can make T cells, immune cells that attack cancer cells from iPS cells. So we want to help patients suffering from cancers as well. Because I lost one of my best friends like 3 or 4 years ago because of cancer. So I really wanted to help cancer patients as well. Yes.
So I have to ask you, when we spoke earlier in advance of this conversation, a couple of things came up that I really want to surface here. So the first one is, in terms of application, so you said clinical trials are beginning, so we really are at this entrance point as you described it. What about the regulation and what about the cost of these kinds of treatments?
Yeah, those are very important issues. Regulation. So in US, there is FDA. In Japan, we have PMDA. In Europe, you have EMA. And each country, each FDA, PMDA, and EMA are not identical. Actually, they're very different in how they want to regulate. So it's been very challenging because we want to help patients not only in Japan but also in US, in UK. So we have to adjust to each different regulation. It's been challenging, and the cost is also a high hurdle because in theory we can make iPS cells from each of you. For research purpose, it's not so difficult, but for clinical purpose, it's very expensive. At the moment, to make iPS cells from you and from me, it costs almost half a million US dollars. So for helping one or two patients, it may be okay, but we want to help many more. So that's another challenge. So our current strategy is that instead of making iPS cells from each individual patient, we make iPS cells from some so-called super donors. So those super donors has some specific immunological type. So their cells would not cause strong immune rejection.
Yes.
So that's what we are now doing. Yes.
Yes. And I can't help but ask you, in the context of the regulation, of this diversity of regulation across the globe, I'm guessing that you would advocate for a more uniform
Yes.
approach to regulation.
Yes.
Can you imagine a day like that when we would be more aligned globally?
I really hope so. Like 2 years ago, there was a alliance forum of all regulatory activities in Japan, in Kyoto. I attended that meeting and I gave a talk. So I tried to persuade all of them how important it is to have a uniform, united regulatory system. Otherwise, it's a waste of time and waste of money if we spend many of our time and many of our money in each country.
Yes.
We have to prepare new data for each country. It's really a waste of time. And patients are waiting for new therapy. At the moment, like some wonderful therapy is available in US, but not in Japan. It's still happening in 21st century. So sometimes we have to send those patients to US. It costs more than $1 million US dollar. So we really want to stop it.
Yes.
Yes.
So we talked about science and clinical application. We talked about regulation. We talked about cost. I can't possibly let you go without talking about the ethics. So, of course, embryonic stem cells, we talked about obvious ethical considerations. iPS, cell-based therapy, has been hailed as free of these kinds of considerations, but things are never black and white.
Exactly. So my biggest motivation to make iPS cells was to overcome the ethical issue of human ES cells. That is, to use human embryos. So when we succeeded in making iPS cells, I was very happy. Well, now we can avoid the usage of human embryos. I was happy for 1 week. Then I realized, wait a minute, we may overcome one ethical issue, but we have generated new ethical issues. Not one, actually, multiple. Or for example, we can make iPS cells from your skin cells or from your blood cells. From your iPS cells, at least in theory, we can make sperm and we can make eggs. So that means we can make a new life out of your blood or skin cells. So it's a huge ethical issue. We maybe help many people suffering from infertility.
Yes.
But creating a life from your blood or skin cells is something you cannot simply do. So, and also by injecting human iPS cells into like pigs or any big animals, we actually, in theory, we can make human organs in pigs or in any big animals. So it may be very helpful for patients suffering, patients waiting for organ donation, but it's not that simple. Should we really make organs, human organs in animals? So those sorts of new ethical issues came to me, and I was actually, in a sense, panicked. I thought I was doing something good, but I realized potentially I was doing something dangerous. So that's so we, as a director of our research institute, I decided to have a new research division focusing on ethics. So we have 5 or 6 ethicists in our institute.
Yes, it's so important when considering research advances of this kind that one balances the potential benefit with the potential pitfalls. And in an earlier session, somebody said that often or rarely technologies are completely good or completely bad. It's the contexts in which they are deployed.
Yeah, so as you know, any science, any technology is a double-edged sword. It can be good or it can be terrible. And it is our responsibility to make whether it is good or bad, any technology. So I think science has so advanced. Each year we are making progresses. So the current level of science and technology is such that we may end up destroy our Mother Earth. So our science and technology is so powerful. But at the same time, we can make this Earth even better by science and technology. So we are really at a very critical point. Where to go? This way or this way?
That's right. A wonderful, thought-provoking thought to end this incredibly enjoyable conversation with you, yes. Shinya. Thank you very much.
Thank you for joining us today. Thank you very much.
Thank you. It's a real pleasure. Thank you very much.